All right, let's jump right in. We hear constantly about the absolutely mind-blowing power of modern AI chips, right? GPUs that can handle billions of parameters, simulating these incredibly complex systems. And that gets you thinking, with all that classical muscle, are quantum computers even necessary anymore?
And you know what? That is a fantastic question. It's totally reasonable to ask. This isn't just being skeptical for the sake of it. It's a logical thought when you see the kind of hardware we have today. So in this explainer, we're going to cut through all the noise and give you a really clear, hype-free answer.
So first things first, let's actually build up the case for classical computing. I mean, we really have to give credit where credit is due, because the argument that we might not need quantum computers is a strong one, and we're going to take it seriously.
What this whole debate really boils down to is a battle between what we have right now, this tangible, massive power, and what we're promised for the future. On one side, you've got the brute force of classical hardware, GPUs, specialized AI chips. And on the other, you have these almost magical quantum ideas like entanglement and superposition.
And seriously, don't underestimate the classical side. It is ridiculously impressive. Our GPUs and AI chips today can already fake a lot of quantum-like behavior. They can simulate wave equations. They can simulate interference. They can even do a pretty decent job approximating quantum chemistry. So yeah, it really feels like classical computers can do the whole quantum shebang already, right?
So if classical computers are so great, what's the catch? Well, to get that, we need to rewind a bit. The answer isn't just about the hardware we have today. It's buried in the history of the problem itself. Let's take a look.
And here's the kicker. The core problem, this 2 to the power of n thing, was identified all the way back in the 1930s. This is way before the first computer even existed. Physicists already knew that to fully describe a quantum system, the amount of information you need explodes exponentially. So by the time we got our first digital computers in the 60s, they immediately slammed into this wall. And that is what led the great Richard Feynman to his big idea in 1981, decades before the AI boom we're seeing now.
What's so brilliant about Feynman's point is that he wasn't talking about speed. This wasn't about making computers faster. His argument was way more fundamental. It was a hardware-independent truth. He was saying, it doesn't matter how fast your chips get, you were trying to solve a problem using a language that fundamentally cannot describe it.
So we've built up this incredible picture of classical power. It seems unstoppable. But this is where classical computing hits a wall. A hard wall. An unbreakable one.
Because for all that power, for everything we just talked about, for all the amazing things that GPUs and AI chips can do, there is one single crucial thing that they just cannot do.
That barrier, that wall, is quantum entanglement. And what is that? Well, it's this incredibly weird property where particles get linked together, sharing a single existence, no matter how far apart they are. The correlations between them create this complex web of information that you just can't pull apart into separate pieces. There's no classical way to write it down.
And this is the showstopper. To perfectly describe a system with n entangled particles, a classical computer literally needs to keep track of 2 to the power of n different numbers. That number grows so fast, it's just insane. For just 300 or so qubits, you'd need more numbers than there are atoms in the entire known universe. Game over.
Now, I really want you to get this part because it's the most important takeaway. This is not an engineering problem. We cannot solve this with faster chips or more memory. It is a fundamental limit baked into the laws of information itself. You just cannot store the information of an entangled state with classical bits without that resource cost blowing up exponentially. Period.
Okay, so now that we see the wall, we can finally draw a really clear line in the sand. We can settle this debate by seeing what each type of computer is actually for.
So where do you need a quantum computer? Only for those problems where this crazy, deep entanglement is the star of the show. We're talking about things like exact simulations for designing new drugs or materials, understanding weird quantum phenomena, and of course, the famous one, breaking cryptography with things like Shor's algorithm. These are the problems that are stuck behind that exponential wall.
And on the flip side, this means quantum computing is absolutely the wrong tool for almost everything else. Most AI, all of our graphics, most of the optimization problems we face every day, they just don't depend on this deep, complex entanglement. For all of that, our classical hardware is and will pretty much always be the better, faster, and more efficient tool for the job. So what's the final verdict here? What does this all really mean? While it's not about one technology killing the other, it was never a competition. It's about having two very different tools for two very different kinds of problems.
So let's just run through it quick fire. Can GPUs simulate a lot of quantum-like effects? Yes, they absolutely can. Do they get around that core exponential problem? Nope, not even close. So is quantum computing going to replace our laptops? No way. But is it fundamentally necessary for a very specific and very important class of problems? Yes, 100%.
And that really brings us to the one sentence that sums this all up, completely free of hype. The reason we need quantum computers has nothing to do with speed. It has everything to do with information. It's a special kind of tool, built to handle a type of information that our powerful classical world simply doesn't have the language to write down.